Okay, so we finished the first two, define and limit, and we know that, okay, we know limit and define, there's no connection between each other, and then they can both exist, both not exist, one exists, one not exist. Okay, so the next definition is continuous. Okay, continuous is decided by define and limit. Okay, so if a function is not defined, you don't need to think about the continuity. It's not going to be continuous at that point. If a function is not limit exists at that point, don't think about the continuity at that point. It's not going to be continuous at that point. Okay, so it must satisfy the first two conditions: is fx is defined and f limit defined. Limit exists. Okay, so that too is the prerequisite. You must have those two first, and then we can consider about the continuity. Otherwise, just don't think about it. It's not exist. Yep. It's not continuous because it's not defined already. Okay, the limit may exist, but it's definitely not continuous. But it doesn't say that when you have the limit, when you have it defined, it will definitely be continuous. Okay, it will be it's not going to be like that. Shh. Stop talking, girls. And there's a third condition. Okay, it's a very interesting condition. You may think about why there is a condition like that. I give you a counter example, which is follow the first one, follow the second one, but the third one failed. But like it's a very special case. Is the third requirement is the limit and the define must be the same value. Okay, the limit and the define must be the same value. You may think about, well, it should be the same value. Okay, it should be the same value. But in some extreme case, it's not going to be. Okay, it's not going to be. So have a look at the first graph. I'll give you 3 counter examples. They not satisfy 3 of each of that. Okay. So for the first one, is it defined? Is it defined? You can see this. That's an open circle here at 0. So 1 is not defined. Okay. So the conclusion directly made, not continuous. Okay, not continuous. Okay, the second. Is it defined at x equals to 0? Is it defined at x equals to 0? What f0 equals to? 0. f0 equals to 0. Okay, 0. Is that the limit exists? Yes or no? No. Can you see no? Like the function is already a jump here. It's not connect together even. It's definitely no limit for that. But how you can say there's no limit? You not just say limit does not exist. You talk about the left hand side, right hand side thing. So the limit x approaching to 0 from the left hand side of fx equals to 0 because it's go towards that end. Can you see that's the wall at x equals to 0? Going the red path, you will reach the ground floor. Okay, and then you will have lim x approaching to 0 positive side of fx. That gives you 1. Okay, that's the blue path. You will arrive level 1 or approaching to level 1. So lim x approaching to 0 negative does not equals to lim x approaching to 0 positive. So lim x approaching to 0 fx does not exist. When you say want to exist, you just say left equals to 0, right equals to 0, left equals to right, then limit exists at that point. It's exactly the same. So I can make the conclusion now, not continuous. At x equals to 0. So it's not going to be continuous anymore. Already failed condition number 2. 3 conditions must satisfy all of that. Okay, must satisfy all of that. Okay, the interesting one is the third one. Okay, can you see this graph? Just look at yours. Maybe yours is not better print than this here. Okay, this graph is a linear. with the open circle at 0, 1. Okay, this open circle is a 0, 1. Okay, it's an open circle. I make it open here. And at that point, there's a dot at 0, 3, which is a closed circle here. Okay, number 1, what is F0? What F0 equals to? 3, it can't be 1. 1 is open circle. Okay, 3 is the point. It's like you dig that point out and then you drag it to the top. Okay, so only that point jump up. So it's a 3. F0 is a 3. Okay, F0 is a 3. So F0 is a 3 now. And think about the limit. This is the wall. Okay, I have a red wall here. That's the wall. And it's from the left, go in the path, and then you stop in front of the wall. Which level you arrive? Level 1 or level 3? That's the wall. Okay, see, that's the wall. Okay, you're going. Okay, think about there's a wall in front of you. Okay, you climb up, like here, go here, go here. Where you stop when you hit the wall? 1. It's not going to be 3. You're not jumping up. Okay, so you're going down here. Okay, you hit the wall. Where is it? 1 as well. So your limit is 1. Okay, your limit is 1. So limit is 1. So what I would say is lim x approaching to 0 of fx, it is 1. Okay, left hand side, right hand side, both 1. So the limit is 1, although the defined value is 3. Can you see number 1 exists, number 2 exists, but number 3 failed. Number 3 failed. Number 3 is f0 is not equals to lim x approaching to 0 of fx. Because one value is 3 and one value is 1. So the conclusion is not continuous at x equals to 0. Okay, so it's not continuous at x equals to 0. There is a set question in year 12 this year for the first SAC. The SAC is prove that this point is continuous. Okay, the question is just a 3-mark question. And the question is prove that point at x equals to 2 is continuous. And then in my class, no one got the full mark because they forgot it. Like even though I say it, it's like about 100 times before the SAC, they just not think that's the important thing. Okay? Even though I said, especially this page, okay, everything on this page, you need to know it, and they not pay attention. So I'll tell you now, this is something will be on the exam and will be asked you to prove. So how you will prove? Where do you think the 3 marks go in? 1 mark is first one. You say the defined value. Second mark is the limit. You talk about the limit, whether it exists or not exist. The third mark will be you state they are equivalent or they are not equivalent. Okay? You need at least 3 things listing there. First is define, second is limit, third is compare limit and define, and then make a decision whether it's continuous or not. Okay, so that's a full proof for continuity. Okay, that's in theory. Okay, that's in theory. If it's not in theory, if you just look at the graph, what's the requirement for continuous? The graph needs to be connected together. Okay, only one requirement. At that point, the graph is connected. At x equals to 0, the graph is not connected. The graph is not connected. At that point, x equals to 0, the graph is not connected. Connected means there's no hole, no jump, like it's very good, like connected, okay? Connect point. At x equals to 0 here, it's not connected. It's an open circle, okay? It's not connect. So on the graph, it's very easy to see it's not continuous, okay, when it's not connected. So you can forget all the theories and you only need whether it's connected or not, okay? But we still need to remember the theory. It can be particularly asked, proof that is continuous. to talk about the continuity for the function below, okay, I just have two functions here. Have a think about this question. Where do you think the point will have some problem? 2, okay? 2 is the connection point. Which point might have some problem? Is the 2. 2 is the connection point. You want to make sure whether it's actually connected or not. Shh. Whether it's connected or not at that point. Okay? If, let's say, one closed circle is here, one open circle is here, they are not connected. Okay? But if you know closed circle is here, the open circle is at the same point, they are connected together. Okay? So what you need to decide is actually the connection point, not any other points. So it's the 2. I will just name those two functions separately. I'll say f1 is 2 minus x. f2 is 4 minus x squared. Okay, and then I'll substitute 2 separately. f1, 2, I will have 0. f2 of 2, I will have 0 again. What you can't do is f0 equals to 0, 0. That is what you can't do. Okay, why you can't do that? Fx is a function. 1x only give you 1 y values. Okay, when you substitute 2, you can only substitute into that function, not the below one, because the below part doesn't include 2. You can't substitute at all. Put the 2 inside. This means 1x gives 2 y values. Okay, gives 2 y values. That's totally wrong. So you can't have the notation like that. You must name them separately and then find the values. Okay, so for the coordinates, for this one is a 2, 0. For this one is a 2, 0 as well. Okay, for this one is a closed circle. For that one is an open circle. Are they connected? Yeah. At 2, 0 is a closed circle around the open circle. Is connected. So the function fx is continuous everywhere from 0 to 6. I'm not including those two endpoints because you can't talk about continuous for the endpoints. There's nothing connected over there. And then the only thing you suspect is the 2, whether 2 is connected or not. And you prove 2 is connected, there's no other problems for that for the rest function as well. If you can't understand what I'm talking about, you can sketch a graph. Okay, you can sketch a graph, sketch this hybrid function, and you can see the graph is connected and there's no problem at all. Okay, the last one is connect at 3. Okay, the last one is connected at 3. So I can still go f1x equals to 2x, f2x equals to x squared minus 9. And then I will say f1, 3, that is a 6. f2, 3 is a 0. That point is 3, 6. That point is a 3, 0. That is a closed circle. That is an open circle. So I don't care what other place looks like. In the end, this looks like here. And then open circle here. And x equals to 3 is definitely not connected. Okay, one jump up. Okay, one stay at 0. It's definitely not going to be connected because they are not at the same point even. So fx is continuous anywhere else for -3 to 6 except Okay, so for all the rest, it's fine. From -3 to 6, but only 3 doesn't work. Okay, only 3 doesn't work. Or you can say x belongs to -3 to 6 except 3 is continuous. Okay, that range is continuous. From -6 to -3 to 6 is continuous and excluding 3. And excluding 3. Okay, I have talked about a lot today. I give 3 definitions, define limit and continuity today. Okay, so it's a lot. You need to make sure you understand all of that, and then we'll go back to exercise A next lesson. Okay, that will be easier. This is the most difficult part for this chapter. Okay, that's the most difficult part.